Alright, so welcome back. We're going to learn a couple more rules today, and we're going to see the derivative of one of the more important functions that we'll use throughout the rest of this semester. So let's go ahead and start with the definition of the letter E when it refers to a number that's going to be somewhere between 2 and 3. So what we're going to do is we're going to look at limits of a to the h minus 1 over h as h goes to 0. And if you think about it for a second, if we let h be 0, a to the 0 is 1, and so 1 minus 1 on top is 0, and h below when h goes to 0 would be 0, and so we'd have one of those limits that looks like 0 over 0. And whenever we have limits that look like 0 over 0, we're really curious if they actually wind up limiting to something sensible. And if you try to calculate by plugging in of values, you'll see that the limit as h goes to 0 of 2 to the h minus 1 over h, and the limit as h goes to 0 of 3 to the h minus 1 over h go to 0.693 and 1.099 respectively. So these are limits you can compute, and we'll actually see exactly what they are later, but we can see that one of these is less than 1 and one of them is bigger than 1. And so we're kind of curious, what would you want to put instead of 2 or 3 so that the limit was exactly 1? And we know it's got to be between 2 and 3, and you can check a bunch of other numbers to see that this is true. And so the curiosity is, what should we call it? And we call it E. So E is the number such that that limit, the limit as h goes to 0 of e to the h minus 1 over h, is 1. So E is the very, very special number somewhere between 2 and 3 that makes that limit exactly 1. And since E is a number, just like we can have the function 2 to the x or 3 to the x, we can also have the function e to the x. And so we can ask ourselves, well, what's the derivative of e to the x? And so if you write out the limit definition of the derivative of e to the x is the limit as h goes to 0 of e to the x plus h minus e to the x all over h. Both of those terms up top have an e to the x in them, so we can pull the e to the x out, and you're left with the limit as h goes to 0 of e to the x times e to the h minus 1 over h. Now, e to the x doesn't depend on h, and so we can actually pull it out front. And then we have that limit from before. The limit as h goes to 0 of e to the h minus 1 over h, well, that's just 1. And so the derivative of e to the x is e to the x. And that's really weird. What it means is that whenever you pick a value of x, the slope of e to the x is just e to the x. So the slope at 2 comma e squared is e squared. The slope at 1 comma e is e. And the slope at 0 comma 1 is 1. And so, if the slope is always like the y value, it's like saying that your speed is always exactly equal to how far you've driven. Okay, so that's neat, but let's talk about two of the most important derivative rules that we haven't gotten to yet. And so, here we're going to talk about, well, what happens if you take the derivative of the product of two functions. So f and g are functions, and we're taking the derivative of the product, f of x times g of x prime. Well, the definition is, it's the limit as h goes to 0 of f of x plus h, g of x plus h, minus f of x, g of x, all over h. Now, if you look over there, I've written a very, very fancy version of 0. And you can always insert 0 as an addition anywhere, because adding 0 doesn't do anything to a value. And so I'm going to go ahead and insert that between f of x plus h g of x plus h minus f of x g of x. And then what you should notice, what's sort of important, is these two have a common factor of f of x plus h, and these two have a common factor of g of x. And so I'm going to go ahead and factor those out, and on top of that, I'm going to split my fraction into two fractions. Now if I go ahead and I rewrite these so that I pull out the f of x plus h, then this is going to look like the derivative of g of x, and this is going to look like the derivative of f of x. And so the derivative of f times g is f of x g prime of x plus g of x f prime of x. This is known as the product rule. So that's good for the product, but how about the quotient? What if we have one function divided by another and we want to take the derivative? So again, we just go ahead and write out the definition. And so we have f of x plus h over g of x plus h minus f of x over g of x, all divided by h. Now in order to get rid of the fact that we have all these fractions, we're going to clear out the numerator by multiplying top and bottom by g of x and g of x plus h. And that gives us this expression. Now again, in order to continue, we're going to need to enter a very, very fancy version of 0. And so here in red is the fancy version of 0 that I'm going to put in. So my limit as h goes to 0 of g of x f of x plus h minus g of x f of x plus g of x f of x minus f of x g of x plus h all over h g of x plus h g of x. If you look, these have a common factor of g of x, and these have a common factor of f of x. And so just like before, we're going to go ahead and factor. And now, this and this look like exactly what we need for f prime and g prime respectively. And so what we get is that the derivative is g of x f prime of x minus f of x g prime of x all over g of x squared. And so this is called the quotient rule. And one way to remember the quotient rule is by thinking of a fraction as being the high part and the low part. We used to like to say the derivative is low d high minus high d low over low squared. It's the lower part times the derivative of the upper part minus the upper part times the derivative of the lower part over the lower part squared. So here's just a list of rules. These are all of the rules that you've learned so far. I've just put them on one slide so that if you're taking screen captures, you can have them all written down in one place. Now let's go ahead and do an example. So here's a function, which is the product of the cube root of x minus 1 and x to the fourth plus 1. And I want to know what is the derivative. So we recognize that this is a product, and so what we're going to do is we're going to use the product rule. So step 1 is to go ahead and rewrite this in the following way. So after you've gone ahead and written it in this way, we can start actually taking the derivatives of the cube root of x minus 1 over here and x to the fourth plus 1 over here. Both of those are sums or differences, and so the next set of derivatives is written like this. The derivative of the cube root of x minus 1 is just the derivative of the cube root of x minus the derivative of 1. And the derivative of x to the fourth plus 1 is the derivative of x to the fourth plus the derivative of 1. Now we just have to use the power rule. And here is the power rule. We get 1/3 x to the 1/3 minus 1, and the derivative of 1 is 0. and we get the 4x to the 4 minus 1, and again the derivative of 1 is 0. And so our final answer is going to be 1 over the cube root of x squared times 3, 1 over 3 cube root of x squared, which is the same as 1/3 x to the negative 2/3, and multiply that by x to the 4th plus 1, plus the cube root of x minus 1, all multiplied by 4x cubed. So here's another one. Compute d dx of x squared minus 1 over x squared plus 1. Here you'll see that what we're computing is the derivative of a fraction. And so, since it's a quotient, we need to use the quotient rule. And so the derivative of the fraction is the bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. If you go ahead and start writing out what all of this means, you'll find that the next step is to distribute the derivative across the subtractions, and then to use the power rules. We can then go ahead and distribute everything and combine into one nice term. So the derivative of x squared minus 1 over x squared plus 1 is 4x over x squared plus 1 squared. So that's it. Go ahead and practice taking some derivatives using product and quotient rules. Practice using the derivative of the exponential function. And I will see you next video.